Okay, so I know you guys are ready to start solving some half-life problems. I'm super excited. Okay, so half-life, you guys, this basically tells us this is the amount of time it takes for a substance to decay to half of its original amount. Okay, or half of the original size. So we have a formula that predicts, given a half-life time, so how long it takes something to decompose to half the size, okay, we can predict things about in the future about our compound. Okay, so in this formula, n of t equals n sub 0 times e raised to the negative kt, sorry guys. N of t is the end amount, n sub 0 is our initial amount, so the amount that we start with. K is our decay constant, which we will have to solve for the k value, and we will be rounding that to 4 decimal places, and t is going to be the time given to us in the problem. So, when we start these problems, okay, what we're going to look for first of all is an initial amount and the half-life, which this will be the time we're going to use that first. And don't forget the half-life time is the time it takes an object to decay or break down, okay, to half of its size. Okay, so it tells us how long it takes it to decay or break down to half of the size. And this will help you to solve for K. Okay, and we'll talk about that last sentence in just a moment. Okay, and then we'll talk about this part in just a second. Okay, so in our example 1, if you see it's a 2-part problem, so we're going to start on this side, and we'll have some things that we look for on this side, and once we find these things, it will help us to actually solve the problem. So let's get started. So it says a paleontologist uncovers a fossil of a saber-toothed cat in California. He analyzes the fossil and concludes that the specimen contains 15% of the original carbon-14. Okay, which carbon-14 is just a chemical compound, so this compound is found within this fossil of the saber-toothed cat. Okay, and it says carbon-14 has a half-life of 5,730 years. So that means it takes 5,730 years for this carbon-14 to break down to half of the size it originally started with. And then it says determine the age of the fossil. And we're going to round our answer to the nearest fossil age. Okay, so the first thing we're going to look for is our n sub 0, which is our start amount, in this case of the carbon-14. And then we're going to look for a half-life, which that will be the time we use on this side. Now we're going to use a different time on this side, so be careful. Okay, our n of t value, okay, since we're dealing with half-life on the first side, okay, our start amount is the initial amount, and since we're dealing with the time it takes for the object to break down to half of its size, the end amount will be half of the start amount. And then we'll be solving for k. So let's see here. I'll go ahead and color code since you can't really see at the top. I'll go ahead and label everything. So we have n of t equals n sub 0, which mine is in green, n sub 0 times e. Now remember you guys, e is not a variable, it's just that constant number we talked about, that 2.71, that is what our e is. And then to the negative, be careful, negative k times t. So we do have a negative in our exponent, so watch yourself. There is a negative somewhere. Sorry guys. So our negative k times our t. Okay, so the first thing we're doing, we're looking for our n sub 0 or start amount. Okay, which if I look through the problem, it doesn't tell me how much carbon-14 the fossil originally had. Okay, it does not tell us the start amount. When this fossil was discovered, it does not tell us how much carbon-14 was in the fossil. It does tell us that it contains 15% of its original carbon-14, but it doesn't actually tell us how much carbon-14 it has. Okay, so this is what we're looking up here. Okay, so if the initial amount is not given, use 1 as your start amount. Okay, so since we don't really have a start amount that the fossil initially had, okay, we're just going to use 1 as our start amount. So in this case, our n sub 0 is just a 1. Okay, which that's not really common. Okay, in all the rest of the problems, our n sub 0 will have an actual answer. So this one's a little trickier. Okay, now we're also looking for our half-life time. So I'm looking for the word half-life. Okay, so when I look through the problem, I see the word half-life right here, half-life. Okay, and that half-life is going to be the time that I'm using on this side. So this right here, this 5,730 is our half-life time, and it will be our T for the first side. So I might write T sub 1, that's the time I'm using on side 1. Okay, and then after that, we'll find our end of T and just a minute our end amount. And what we're going to do with this information is solve for K. So let's get going. Okay, so our end of T is this, if this is talking about, this is how long it takes for the original substance to decay to half the amount. Okay, if our initial amount is 1, our end amount is half that amount, which is half. Half of 1 is 1/2. So in this case, our end of T is 1/2. Which again, this is this very special case. The rest of the word problems will not be like this. Okay, so we have 1/2 equals my n sub 0, which I didn't know, so I just made it a 1 since I didn't know what the SAR amount was. All right, times e to the negative k, which I'm solving for negative k. I don't know what k is. That's what we're solving for. Solving for k. All right, and then the time we're using is the half-life time. So the time is that 5,730. Okay, so we need to solve this bad boy for k at first. So I need to move everything over but my e and my exponent. Okay, which I need to move 1 over, which technically I don't really even have to move 1 over. 1 times anything is itself. So technically, my answer on this side is all that. Okay, so I don't even really have to move it over. So currently what I have is 1/2 equals 1 times all that is just what it is. So negative k, e to the negative k, times 5,730. All right, guys, so I need to solve something that is currently in the exponent of my exponential. Okay, which the only way to undo an exponential and get to that exponent is by converting this bad boy into a logarithm. So let's go ahead and do that. Okay, so in this problem, remember the logarithm stays on the same side as the base, okay, which my base is currently on the right-hand side. So my logarithm will stay on that side. And since we have e as our base, remember, we're going to be using a special logarithm, the natural logarithm. Okay, so natural log of base e, which you don't have to write it. I'm not going to write the base because typically we won't see it. Okay, so I'm not going to write it. And then remember, you guys, these two are going to trade places. So my 1/2 is going to jump inside my natural log. Okay, and my negative k times 5,730 is going to go to the other side. So negative k times 5,730, or if you want to put in a parenthesis, you can. Either way means the same thing. Okay, so I need to get k by itself. Okay, so I need to move my 5,730 over as well as this negative, which, since I don't see a number in front of my k, secretly this is a negative 1. So I'm going to move my negative 1 and my 5,730 over all at the same time. So I'm going to move my negative 5,730 to the other side, since this is secretly multiplying to the k. Okay, so my negative 1 and my 5,730 will cancel out. Bam and bam. Okay, so my k value will equal all this stuff, which the only way to get that is to type it in our calculator. Okay, which, remember, up here it says to round k to 4 decimal places, which it says that, where does it say that? Here, sorry. Here it says your k value round to 4 decimal places. So that's what we're going to be doing. Okay, so I'll show you how to type this bad boy into our calculator. All right, so here, let's see if we can get a better look at that. Can you see that a little better? Kind of. Okay, so we have natural log of 1/2. So we have natural log. Now the natural log key. Do you see that ln key beside the 4? That's your natural log key. So we're going to put in that bad boy. So natural log of 1/2, so 1 divided by 2. and then divided by, so I'm going to do another fraction, divided by negative 5,730. Holy hot dog. So this thing is my K value. All right, now something we need to talk about. When you see that e to the negative 4, that means times 10 to the negative 4. This is in scientific notation. Okay, so to get this, we need to move our decimal. If it's negative, okay, we move it that many spaces to the left. If that e number had a positive number, we'd move it that many spaces to the right. So I'm going to take this number and move my decimal 4 spaces to the left. Okay, so let's see here. My K value, we have 1.2. Actually, I'm going to write it over here. Sorry, guys. Need a little bit more space than that, I'm realizing. Okay. So I have 1.2, and I'm going to move that bad boy to the right to the left 4 times. So to the left, to the left, to the left, to the left. That's where it lands. So I'm going to have 1, 2, 3 decimal places. Sorry, guys. Okay. And it says to round K to 4 decimal places. So 1, 2, 3, 4. So I'm going to land at the 1, and the 2 is not going to bump it up. So my K value is approximately 0.0001. So that is K value we're going to be using on the other side. Okay? All right. Alright, so now, after using this information, we're going to use our K value and use some other stuff to help us actually solve the problem. So I know you guys want to actually solve the problem. I know you do. Okay. So, on this side, we're actually going to solve the value. So we're going to use the same n sub 0 value, which my original n sub 0 value was 1. So our n sub 0 is still going to be 1. It says use the K value found on the left. Okay, so my K value that we found was 0.0001. So my K equals 0.0001. Okay, and now we're going to use the new n of t amount or t value, depending on what they give us in the problem. And we're also going to be solving for n of t or t. So if we are using n of t here, we're going to solve for t. If we're using t here, we're going to solve for n of t. So we have to figure out what we are actually solving now. Okay, so let's see here. Let's go back through the problem. Paleontologist uncovers a fossil, yada yada. He analyzes the fossil and concludes the specimen contains 15% of the original carbon-14. So that 15% is an end amount. Okay, it has 15% of what it had from the start. So this is an end amount, which means it will be an n of t. So in this one, we're actually going to have an n of t value, okay, which means we're not going to have a t value. So n of t is going to equal 15% of the original, okay, which if we have 1, 15% of 1 is 0.15, which how I got that, I'll do the work over here. Okay, if I want to find 15% of my original is 1, times 15%, well, if I convert 15% to a decimal, so 15%, I go to the left to convert it to a decimal. So it'd be times 0.15. So 15% of 1 times 0.15 is 0.15. So that's where that number came from. Okay, and let's keep reading. It says carbon-14 has a half-life of yada yada, 5,730. Now it says determine the age of the fossil. So I want to know how old the fossil is or how many years it's kind of been hanging out. So we're trying to solve for a time, and we want to know how old this fossil is. So we're actually solving for the time in this case. So that's what we're solving for. Okay, who's ready to set this bad boy up? Let's go. So our n of t is 0.15. Okay, and that will equal Rn sub 0, which is 1, times e to the negative k, which k is 0.0001. So that will be negative 0.0001 times our t value, which we're solving for. Okay, now this problem is going to flow very similar to this problem. We're going to have to rearrange this into a log to solve for something in the exponent. Okay, and like last time, 1 times anything is itself. So I'm going to rewrite this as e to the negative 0.0001 t. So this will be 0.15 equals just e to the negative 0.0001 t. Alright, so now I have something in the exponent I'm trying to solve for. So in order to solve for it, I need to convert this bad boy into a logarithm. Which, remember, the log stays on the same side of the base. And since we have a special base, base e, it will be natural log. Which I'm not going to write the base, since natural log we normally don't see the base. And then remember, you guys, these two just trade places. These two will trade spots. So the 0.15 is going to hop inside of my logarithm, like so. All right, and the negative 0.0001t will hop to the other side. All right, guys, all we have to do is solve for t, okay? Which, since this is secretly multiplying to the t, the way we move that bad boy over is by dividing. So I'm going to divide both sides by 0.0001, or negative 0.0001. Okay, which those two will cancel and turn to 1. Okay, so let's see what t is going to equal. I'm going to type this bad boy in my calculator. Okay, so we have natural log. I'm going to hit the natural log key, which remember that's beside the 4 button down here. So natural log, can you see it? Let's see, kind of. Natural log of 0.15, so 0.15. I'm going to close up, point, not negative. Close my parenthesis and then divided by negative 0.001. So divided by negative 0.0001. Holy hot dog, look at that time. Okay, and it says to round your final answer to the nearest fossil age. So we want to round it to the nearest whole number. Okay, so when we look at this, we're going to look at the decimal, the 0.1, and since my 0.1 is not above 5, it will not bump my 1 up. So I'm just going to write this down right here. That's my answer. All right, guys, so my time would be, okay, so my time equals 18,971 years. Holy hot dog, that's an old fossil, you guys. So that would be my final answer. Awesome job, you guys. Now, example 2 is similar to example 1, but we don't have this issue where we're not given the initial amount. The next ones will have the initial amount, which is a little different. Okay, so go ahead and you can stop the video now because we're done, and you can start watching the next example problem. It's been awesome, you guys.